Start. I say good morning, everyone. I think it's 8 now. Probably we might wait a couple of minutes more to let people move in. Good morning. Did you sleep well? So welcome to the full-day educational course on diffusion imaging. And today we're going to have a very rich program going from the basics to most advanced application of diffusion imaging. With a speaker coming from many places, from London, from Netherlands, from United Kingdom, and then where is it? The rest? Okay, Denmark, Germany, US, and Australia. So really from everywhere. I think the plan for today is to give some lecture first, and then maybe during the coffee break, if there are questions, or before the coffee break, sorry, we can actually have a discussion with two or three talks together, or have a major debate at the end of the session in the morning, one major debate in this afternoon. That is the plan. But if you really have any pending question, just feel free to raise your hand and come ask questions. I think the program is quite relaxed, so we have time for questions at any moment. All right, I think we can start. And let me introduce the first speaker, is Zoltn Nagy. Unfortunately, Carla Miller is not able to attend today due for family reason. So Zoltn Nagy from University of Zurich is giving his talk instead, and the talk will be diffusion magnetic resonance imaging application and data acquisition. Okay. Thank you very much.
Thank you. Good morning. Can you hear me? Does this work? Okay, great. So I'll come down here. I find educational without actually pointing at slides. I actually wish we could write somewhere on a blackboard or something. But anyway, you don't need to see me. I will mostly point at this slide, none of the other ones. So I'm Zoltn. I studied physics, and then I did some neuroscience, and I've been working as an MR physicist for about 12 years now. So I'm a late replacement for Carla Miller. And after I accepted the challenge, I got her slides, and I realized that she gets through a lot of things in a very short amount of time. I'm not sure if I can do that. That's my first disclaimer. And the other one is, since I rushed the slides so much, I didn't put in any references. Okay, so I apologize to all the people whose work I quote, and it's not referenced. Neither did I reference my own, so there will be no references in there. So sorry about that. But a lot of the things I talk about are out there now. They're nothing brand new. They've been referenced a lot of times. I think those are the disclaimers. Right, and I wanted to ask a few things. How many of you know what a spin echo is? Okay, about half. The diffusion law, fixed diffusion law? Not many, okay. Few. And what about EPI acquisitions, echoplanar imaging? Okay, again, about half. All right. So at the risk of some people getting some more morning sleep, I will go slow, and I will do the basics as well. Just to have the rest of the day, I think a lot of the things that I will talk about will be repeated, which is good, or built upon. So I think it's better to go away from this talk with a little understanding than a lot of confusion. Okay, so some of you can sleep some more, and with the rest of you, we start. So I usually start with this image now. It's sort of MRI, and I think everybody recognizes this as fiber tracks of the brain. MRI is sort of popular science now. I got this picture out of this magazine, Wired, and the cover, this is the, I don't know how many of you recognize him, but he's the head designer of Apple. So we were in the same issue. And also, this is a recent album cover, The Muse, the rock band. So they had this as their album cover for whatever reason, I don't know. I don't know if the songs were about fibers, but anyway, they chose this because I guess it's a good-looking image. So anyway, we're talking about something that's really in the public domain now. So we should know about it, perhaps. This is just a postmortem brain. Most of you, or maybe all of you, will recognize it. You know where the white matter is, gray matter, some subcortical gray matter, those holes over there are the ventricles. And you know, a lot of this has been done post-mortem under microscopes or just like this, and characterized. You can get very thick books of atlases of the neuroanatomy both micro and macro anatomy. And the cool thing, or the reason that MRI is so popular is you can do this non-invasively. So things where, you should see white matter, those are bright, and things where you should see the gray matter are looking darker. But the wonder of MRI, or the reason it's so widely used, is that you can change the contrast. So this is the same brain. Maybe you recognize that it comes from the same subject. It's in vivo. The contrast looks different. Doesn't come out so well on this projector, but here you see more subcortical gray matter than here, but the gray-white matter contrast is worse. So anyway, you can change the parameters on an MR scanner, and you can get all kinds of different contrasts. And one of the cool contrasts that we talk about today is the diffusion contrast. And those with a trained eye will be able to tell differences apart between these two images. They are both, again, coming from the same person in vivo in the same session, just one after the other, maybe 2 seconds apart, maybe 10 seconds apart, more like. But you can see this is dark here, whereas this is bright here. This is bright here, whereas this is darker there. And this is, in diffusion imaging, a lot of the information comes from between images. So you have to collect a lot of images to measure diffusion in the brain in 3 dimensions, so get the 3-dimensional diffusion profile. But anyway, this is what we want to get to. We want to understand how this happens by the end of this talk, okay? This is our aim. And the way I'd like to get there will be to talk a little bit about the diffusion process, just the underlying physical principle, how we go about measuring it with MRI. I was asked to talk a little bit about artifacts. It's not always, free lunch or never a free lunch with MRI. So the reasons that allow us to measure diffusion also sort of predispose us to different artifacts, and I will talk about a few of them. I thought we would have time for questions, but apparently the questions will be at the end or around noon, halfway through the session, so maybe we skip those. Okay, so let's talk about the diffusion process. A lot of the times when you get to this point, the talker or the journal article will show you a bottle of water or something with a drop of ink in there, and they show how it diffuses in 3 dimensions within the bottle, and it's more or less isotropic, meaning that it diffuses in all directions similarly, so you get some sort of a sphere after a few minutes and a bigger sphere after a few more minutes. So that's cool, that's a diffusion process, but that's not, it's slightly misleading because in MRI we don't have any ink to drop into our brain, right? So we have to do some sort of painting of the molecules, in this case water molecules, that diffuse around. Okay, so it's not one material diffusing in another, it's self-diffusion. So what we talk about here is self-diffusion. And the whole idea of MRI is how to paint the molecules so that you can follow them around in this diffusion process, and how you can check that they moved a certain distance apart, away from where they started. So that's one important thing that I'd like to point out, that we're talking about self-diffusion. So it's water diffusing in water. So in that demonstration, when you have a bottle of water and you put a drop of ink in there, even before you drop in the ink, there is diffusion in the water. Okay, so the molecules are already going all over the places. By your eye, you can't tell it. So somehow you have to mark them, and that's what we do with MRI. So a few more slides here, some animations about the diffusion process. Let's assume for a second that these circles are you guys sitting in the rows of seats, and I'm standing somewhere here, somewhere in front of you. This is the screen that you're looking at. So if I was, now that it's a European Championship, let's say I was a famous football player, a lot of you would want to do something like this, just run towards me, right? So that's not diffusion process. Bulk flow like this, so all the molecules moving in the same direction, is not diffusion. So blood flow or air flow as you breathe in and out, that's not described by the diffusion process. Okay, so let's reset. So moving in one direction preferentially, not diffusion. Okay, what about this? Some of you moving this way, some of you saying, I don't care about football players, I'm out of here. That's still not diffusion process, okay, because that's, again, although you go in 2 directions, it's 2 preferential directions. So once this person starts going out, they never turn around. So more like a diffusion process would be something like this. You're trying to decide, do I like football players, do I not? I don't know. Maybe I go. No, maybe I come. Okay, I come. No, I go. So that's the kind of process that we talk about. It's still not great. I mean, I didn't have time to animate these little circles perfectly. By the way, do you see this? Is it bright enough? I can barely see it. Does everybody see it? Cool. Okay. So we're talking about some sort of random walk where there is no preferential direction, left or right or up or down, back, forward, nothing. So the particle at every time point goes in a certain direction, which is unpredictable at every time point. Okay, so that's the diffusion process. If the process was not this random, you would not be able to describe it with the diffusion tensor, for example. The diffusion tensor, some of you may know it. It's a symmetric matrix, meaning that certain elements in that matrix are identical, and the fact that it's symmetric, it can only be symmetric if there is no attraction. For example, charged particles cannot be described by that. Okay, so things preferentially go in one direction or the other, no good. So we need a random process, and that's what I try to describe here. So if we have that random process, in this is the corpus callosum, maybe you all know, but I showed you earlier these two diffusion images, and this was dark and this was bright. And the reason was that here there was a large distance that the molecules got away from the start, whereas here they didn't get so far. So this is this white line is supposed to display their sort of distribution after a certain amount of time. You let them start wandering around, and after a while, they either go far or they stay where they started. And diffusion, when they go far in MRI, it leads to signal loss. Okay, so that's why the corpus callosum here is dark and here it's bright. And the reason that you can modulate this, whether you want to see it bright or dark, is how you measure diffusion, what direction. So in this case, the red arrow describes the diffusion was measured left-right. And in this case, the diffusion was measured, this is supposed to indicate that it's perpendicular to the plane of the image. Okay? So in this case, when you measure diffusion perpendicular to the corpus callosum, then you don't get signal loss. When you measure it left-right, in the way that fibers run in the corpus callosum, you get signal loss. And this is because the diffusing molecules can get farther from the starting point or not. Okay, and I think this just shows how this is acquired. If this is your brain, this is an axial slice, more or less an oblique slice, and then this is left-right, and this is perpendicular to this slice. I hope that's clear. So let's talk a little bit about how you write it down in numbers. So now we have some sort of an idea of what diffusion process is. How we write it in an equation. This is Fick's law. He has another one. This is the first law. And it only has 3 components. It's a relatively simple equation. This is concentration difference. So C stands for concentration, and this funky dC dx, it just means this is the change of concentration in the x direction. Let's say left, right here. So if you put a bouquet of flowers over there, the molecules that are responsible for smell would be in high concentration over there, whereas at the other end of the room, it would be low concentration. So there would be a change in concentration from there to there. That's what this describes. This thing is the diffusion. It's J. It's not D, but anyway, it's flux. So if you have a plane in between the left and the right of the room, in a certain amount of time, how many of those smelly molecules get through that plane of surface per unit area of the surface per unit time? That's the unit of that, and this is the diffusion constant, and it's negative. The whole right-hand side is negative because we're going down the concentration gradient. Okay, so we go from high to low. That's why this negative number here, and this thing D is the diffusion constant. That's what we would like to measure with MRI. That's the question in our MRI experiments. And in one dimension, it's a scalar constant. Okay, so it's just a number. It's 5, whatever. So one dimension, of course, is not very very interesting yet. What you really want to do is measure diffusion in all 3 dimensions. And the equation gets a little bit more complicated, but it's still the same idea. The flux. So how much material gets through a certain surface in a unit time per unit area is now a vector. So it's the surface is in the x direction, in the y direction, and the z direction. So you basically a box. You want to see how stuff is diffusing around. This upside-down triangle is just a mathematical notation for doing this change of concentration in all 3 dimensions. So when you do that to C, you get the change in X, the change in Y, and a change in Z. So it's relatively simple. This is, now you have, in 3 dimensions, the concentration difference, the concentration gradient, and you still have the diffusion constant. And my question is to you, if you can guess, will it still be a scalar constant? Or when can it be? We don't have time for discussion, but maybe you can guess that it gets more complicated in 3D. If the diffusion is in water, like we talked about earlier, then you can still describe this pretty much with the constant, because in all directions, it's the same diffusion constant. So there is no preferential diffusion direction. Then it's a constant. If you have preferential diffusion directions, then you can't describe it with a constant anymore, and you have to model it somehow. One of the basic models is diffusion tensor, and I would talk about that a little bit. You will hear a lot more about it during the day. But then the point is that in the diffusion in the x direction depends on not only in the concentration difference in the x direction, but it also depends on the concentration difference in the y and the z directions. Okay? So, for example, just some analogy. Let's say earlier when I said everybody is running towards me, or some of you will run towards me or diffuse towards me. People in the rows will make it, it will be harder for you to get because you have to step over the steps. People who can run down the aisles will get here sooner. And the point is that you can decide, do you come here coming over the steps, or sorry, the chairs, the rows of chairs, or do you go to the left and then come over? So you can get here into the same position by also knowing what the diffusion constant is left-right, not just towards me. Okay, so that's why coming here, sorry, y would be, earlier we said this is y. So y would be dependent not just on the concentration difference in this case, and the diffusion constant in this direction, but also in the x and z. You could maybe jump over, come on the ceiling, whatever. So anyway, each of the diffusion processes in each orthogonal direction depends on all the diffusion processes in all directions, okay? And if you this looks kind of complicated, but if you write it down in matrix notation like this, so this is concentration difference x, y, and z, and this is then the diffusion tensor, okay? And this is what we try to measure. In diffusion tensor imaging, you will want to measure these elements in this matrix, and I said earlier that this is a symmetric matrix. What I meant by that is outside of the diagonal, the symmetric elements are identical. So xz and xz and yz and yz and yx and xy, they're identical. Okay, so that's because the diffusion process is random and no preferential direction. It's not charged particles. They just go left and right or up and down with the same probability. So this is not the only model for diffusion, and actually it's quite restrictive, a model for complex tissue like the brain. But anyway, it's a very good first approximation, and you can generate very, very good-looking images with it. If you measure the diffusion tensor in every voxel, and then you display it as an image, this is what you get. And I'd like to point out a few things. This was the diffusion constant in x, y, and z direction. And note that it's always brighter than gray. So these are always positive numbers. There is no negative diffusion. There is no negative diffusion constant. Okay, the diffusion constant itself is a positive number. So these things have to be larger than 0. The off-diagonal elements, which are the cross term between the x and y axis and y and z axis and so on, they can be both positive and negative. And this is kind of cool. If you recognize this again as the corpus callosum, you can see that the xy direction, this one, is bright, whereas the perpendicular direction to it is dark, and it's actually negative. Okay, so the off-diagonal elements can be both positive and negative, whereas the diagonal elements can only be positive. The diagonal elements tell you those are the physical constant that you measure, and there is no negative diffusion. If you add up this, so the mean of this of these three elements, the diagonal element, just calculating them all or adding them up is called the trace. And if you divide that by 3, so the mean of these is called the apparent diffusion coefficient or diffusion constant. Okay, so that's what you often display as an image, right? Or you can do voxel-wise statistical analysis on it between different groups. Whereas the off-diagonal elements will tell you about how the diffusion process is sort of rotated around, how the tensor or this ellipsoid is rotated around in 3D space, and those can be both positive and negative. From these elements, you can also calculate things like fractional anisotropy, or from this matrix, you can calculate things like the preferential diffusion direction. You will hear about it more today, like the eigenvalues of this tensor. There are 3 of them, and the biggest one is often the largest eigenvalue is often associated with the principal direction or the preferential direction of water, and that usually aligns with the fiber tracks, in the direction of the fiber tracks. So it's very useful for us to non-invasively check which way fibers are oriented in the brain. But I will not talk about it much more. I have another job to do. I need to tell you how to do this measurement somehow with MRI. And I told you earlier this is sort of a self-painting, self-diffusion process. I just wanted to point out that diffusion as an effect on the MR signal is nothing new. It was published in 1954, soon after the discovery of the NMR technique. They already realized that diffusion affects the MR signal. This person, Purcell, he got the Nobel Prize for NMR, so he knew what he was doing. And basically, diffusion degrades the MR signal, the available MR signal. So usually, you don't want diffusion to happen because you just basically reduce your SNR. But what they realized, which is really cool, is that the signal loss, the amount of signal that you lose from the available maximum, can be related to the diffusion constant of the sample, and that's why we use this method. So this was mostly used in NMR or in spectroscopy until imaging started, and I think 1986, Denis Lebihan had a paper about how to use this in imaging, and then this whole diffusion MRI started. But this is the seminal paper that you may want to know. And this is strictly educational. How many of you know how sequence diagrams look like or how to read them? Okay, maybe about 1/3. So we go through it. I say strictly educational because you would not actually get any signal out of this sequence if you programmed it. But let's see. On the x-axis, so left to right, you have time. This is for every one of these lines, it's time. And the different lines just represent different parts of the MR experiment. This is echo, which is just basically signal collection. These are the gradients in x, y, z coordinates. And they will tell you what amplitude the gradient is. So the height of this box tells you, so a gradient, I told you earlier, is like if you have a flower over there and the molecules that we sense with our nose are high concentration over there and low concentration over there, that's a gradient. So going from high to low, it doesn't have to be linear, it can be exponential or whatever, but usually it's monotonically decreasing. So one way or another you will go down from a high to low. This is really annoying. No, that doesn't work. Just a sec. So what we're trying to say here is that the height of this block is just how big that concentration gradient is, okay? That's just the height. And the length of it is how long the concentration gradient is on. So I can turn it on and then turn it off. So here I turn it on, there I turn it off. And if it was higher, it would be a steeper gradient. And if it's lower, then it's the shallower gradient. That's all these represent. Phase encoding is usually represented like this. We don't have time to go into it. I put it there for reference. This is important. RF, this is how you excite. This is how you inject energy into the sample, which you can later measure out. So you inject energy here, and you measure it out here. And usually you need a slice select gradient. Just to get a single slice, you will have to have a gradient in this direction. So this is the basis of these sequence diagrams. I had to show it because I want to show you how diffusion sequences work. But I think that's all about those, yeah. And one more equation for today. This is the Larmor equation. This is also the basis of NMR, how we get the MR signal. And it's very simple. This is the magnetic field. This is the gyromagnetic ratio. And this is a frequency. So some sort of periodic process, whatever it is. So often it's called spin or what is it called? Precession, yeah. Often it's called precession, but anyway, the fact is that it's something periodic. Something happens periodically, and the frequency of that process depends on the magnetic field and this gyromagnetic ratio. It's a very simple equation. It's a little bit like your salary at the end of the month. This is the salary, and then this is how many dollars you make per hour, and this is how many hours you worked. That's it. So it's a linear multiplication. So this thing is constant for hydrogen, which we usually measure in NMR. So we don't really modulate that. Sometimes you can modulate it, like hydrogen in fat molecules have a different frequency somehow than in water molecules. But anyway, let's assume that it's constant for now. And this is the magnetic field. So if you want to modulate the frequency, all we have to do is modulate the magnetic field. And the way we do this, you probably guessed it, is with gradients. So you put somebody in a 3 Tesla magnet. If this is perfectly 3 Tesla, the frequency will be identical in the whole body, or as long as the body is in a 3 Tesla field. So if you want to modulate the frequency to get some information out of it, then you have to modulate the magnetic field. The gyromagnetic ratio stays constant, and the way you do it is gradients. So in this case, it's a magnetic field gradient, which is, again, like this. It's high at that end of the room and low at that end of the room. Usually, you hope for it to be linear in this case, but that's all you do. Okay, so the frequency is modulated by a magnetic field gradient. And I think that's the last equation for today. So if frequency is modulated, please just pay attention to the top for now. If frequency is modulated by a gradient, then you can do experiments like this. You have 2 water molecules or 2 hydrogen atoms at this x0 position. You put on a gradient, which means since they are away from 0, this gradient will increase the magnetic field locally. So that means they will actually spin faster, right? The frequency will be higher. And I just represented that with this half arrow. So they go half a circle ahead of their counterparts that would be here. So this is, let's say, 3 Tesla. This is 3.1 Tesla, just for sake of argument. Okay? And then you turn this gradient off, wait a little bit, and during that time, one of the particles, one of the atoms stays at x, the other one goes to x0 and x1. So when you turn on a negative gradient, so instead of like this, now it's like this. This one, which stayed at the same place, instead of going faster by half a turn, it will go slower by half a turn. Okay, so this and this, these 2 processes will cancel. Whereas in this one, which went forward by half a turn, then moved to this position where the gradient is higher, where the magnetic field is, the gradient is the same, but the magnetic field is higher here. Therefore, it will go back not half a turn, but a full turn. Okay? So that's the whole idea in an MR diffusion measurement, that things that move around will not be able to be, you will not be able to rephase. That's the sort of the term. This way, you get half a, let's say, 180-degree phase advance. This is a 180-degree phase delay. But here, 180-degree phase advance, 360 phase delay. So you didn't cancel this gradient didn't cancel the effect of this gradient. Okay, so this one got back to the original phase, and this one didn't. And things that are out of phase, maybe you know this, will not produce a signal. So it's you can think of it as vectors. So if the 2 of us, me and one of you, pull on a crate both in this direction, then we can move it. If one moves it in this direction, one pulls it in this direction, the other pulls it that direction, nothing will happen. So vectors, the way you add them, they have to point in the same direction. Or am I running out of time? Cool. Okay. So vectors, we have to point in the same direction to add up. The direction of them matters. So if these things don't point in the same direction, you will not get the same effect, the same sum effect, and that's the signal loss that I talked about earlier. So diffusion leads to signal loss in MRI because the molecules that move around will have all kinds of random phases, okay, and they don't add up. It's almost like all of us trying to move this very simple, very light chair from over there to over here, but we all pull in all directions. It will not move anywhere, right? So the same thing happens with the MR signal. When the little molecules, the little vectors in them which are spinning around, if they point all directions, we can't measure the signal. That's all there is to it. So this is the very simple thought experiment. If I represent it now in an MR sequence, you have to excite your slice. Then you put on a gradient. During this time, you will get some sort of a phase advance. So every position in space from there to there will get a certain different, very distinct phase advance. Then you turn that gradient off, again 0, and then you turn it back again with the negative polarity, which is represented by this line. And everything that stayed stationary in this dimension will rephase its signal, and everything that moved around will lose its signal. So when you read out the echo, which we talked about earlier, this signal will be smaller if there is large diffusion, and higher if there is low diffusion. Okay, it's opposite. A high diffusion constant leads to a large signal loss. A low diffusion constant means that you keep the original signal. So this is almost right. We talked about spin echo earlier. What actually happens in MR experiments, for whatever reason, we can talk about it maybe in the discussion period, is that in between the two gradients, you put in a 180-degree refocusing pulse. And with refocusing pulses, or these MR diagrams, when you think of RF, you always read backwards. Okay, so there is this 180-degree pulse. What it means is that everything that happened here is inverted. Okay, so anything that happened before this, all the way to that point, is inverted. So these phase advances by this 180-degree pulse are actually phase delays. Okay, so the arrow here is pointing from left to right, rather than once you turn this on, it will point from right to left. Okay, so in order to cancel the right to left, you need a left to right again. So this one had to go from negative to positive. So rather than one positive and one negative gradient, you have two positive gradients and a refocusing pulse in between. When you have a 90-degree pulse and a 180-degree pulse in an MR sequence, it's called a spin echo. If you want to read up more about it, that's what you're looking for. And most of the diffusion experiments are spin echo experiments. Yes, I think that's all I need to tell you about that. And this is now how it looks like, the MR measurement. Let me go back. So you will need more than one measurement, and once you do this whole experiment without the diffusion gradients, and several times, as many as you want, some people do it all the way up to 256 diffusion directions, you will measure with gradients. And the gradients can point in this direction, or in this direction, or somewhere in between, this way, that way. So in all 3D, all dimensions, you can point vectors to. Okay, and the way to do it is just you combine gradients on the 3 axes, the slice select direction, the frequency, or X, and the phase, or Y direction. So you would have these red blocks also on these axes. But anyway, when you do it without the gradients, without the diffusion gradients, you get this type of a signal, which is a T2-weighted signal. You can see that the cerebrospinal fluid looks dark on it. And then you will have in cerebrospinal fluid high signal, and somewhere in white matter somewhat lower signal. This is S0, that one over there. And what you do then is turn on these diffusion gradients. It's a similar diagram, different axes, but anyway. And when diffusion gradients are on, you will have signal loss in areas where you had high diffusion, so free diffusion in the ventricles. You will have signal loss there, and you also have signal loss in the white matter, but not so great because the diffusion there is restricted with all the tissue that's around. Okay, but this is actually a log signal. So if you take the logarithm of both sides of this equation, then you get a linear plot, and the slope of this plot will be the diffusion constant. The b-value, which is a very, very important parameter, can be calculated from things like how long a gradient is on, what the distance is, what the time is between the two gradients, and what amplitude the gradients are. Okay, so if you type in your sequence, in the scanner, I want the b-value of 1,000, the scanner will somehow set up these gradients to give you 1,000, but you don't always know whether you don't always know the length, the distance between the gradients, or the amplitude. But if you want to really control your experiment, you might want to know it. Okay, so but those are the parameters that are responsible for the b-value, and that will tell you how much of a signal loss you get for a certain diffusion constant. That's about it. For a tensor, you need to measure at least one of these and at least 6 of these, because we have 6 unknowns in a tensor. There are 9 elements. It's a 3x3 tensor. Apart from the diagonal, there are 3 more unique elements. I told you that it was symmetric. So you have to have, since there are 6 unknowns, you have to have at least 6 measurements and a reference. Okay, so that's how you would do a very simple MR experiment. And now I want to talk to you a few artifacts that can occur. I think maybe I have to go up here now. How do I start a movie? Can somebody please start a movie? I don't have a mouse up there. I don't know if this does anything. So one of them is, one of the artifacts that will happen is due to eddy currents or eddy currents artifacts. We can talk about it some other time. Just memorize the word eddy. And what happens is that these large diffusion gradients, you can't just turn them off in 0 time and then turn them off in 0 time. They will linger. There it is. They will linger in time. And actually, while you read out your MR data, they will be affecting the magnetic fields that you want to put on for reading out the data. But this unknown eddy current effect will distort your images. So if you look, these are 3 different scanners, and one scanner twice. And if you look here, my hand is not steady enough, but if you try to look in one of these voxels, you can see that the tissue actually jumps in and out. You can see that the shape of the brain changes from direction to direction. By the way, the movie is the same slice, and the diffusion directions are changed in 3 dimensions. Okay, so if you want to measure a voxel-wise parameter like fractional anisotropy or the diffusion constant or which way fibers are oriented, you would be hard-pressed to do it in this voxel, for example, where sometimes there is tissue in the voxel, sometimes there isn't. You will get a lot of noise. Okay, and all these 3 scanners, by the way, one is Philips, one is GE, one is, what's the third one? Siemens. And they all jump around with a certain diffusion sequence. The one that I described, it's very difficult to get images which are congruent. This is the same scanner as that, the different type of MR sequence, which I think is coming up here. So rather than a single 180-degree refocusing pulse, you have 2 of them, and you have 4 diffusion gradients rather than 2. Okay, because you have both positive and negative gradients, you can cancel these eddy current effects. So this one, this sequence produced the final image, which was not so jumping around. This is one way to deal with it. There are other ways. So, for example, FSL has an eddy. 1 minute. Okay, has an eddy post-processing tool that can also help you. This is another thing. If you measure diffusion, you can do it at home. You put a water bottle in your scanner, and you will see that the diffusion constant will not be identical in the whole water bottle. The reason is that the gradients, as I said, it should be linear. They are not really linear, actually. In physical space, it's very hard to play out linear gradients. So you can do this experiment. I did it on 2 different scanners. This had highly nonlinear gradients, and this one had highly linear gradients. So when you buy a scanner, just throw a water bottle in there and check what kind of diffusion constant map you get. I have one more example, and you can correct for it, of course. One more example. Can we start this movie, please? Thank you. This is a baby, an infant. I don't know how many of you are interested in that. A lot of people are doing diffusion imaging in babies. This is with pulse triggering, and this data is without pulse triggering. You can draw your own conclusions. I only have 1 minute, but I recommend that you do pulse triggering to avoid these artifacts, because they will, just like the tissue jumping in and out of voxel of interest, you will fit your tensor or whatever diffusion model to artifact. I can't find the word now. I have to rush to artifact the data anyway. And I think this is the final slide. I just wanted to show you this artifact here. Compare it with these 2 images. You see in the anterior corpus callosum, you have a signal loss in these images. And the funny thing is that this was triggered and this was non-triggered. So as I showed you earlier, you're probably better off triggering your diffusion acquisition. You can also test it. Not every scanner needs it, but you can test it easily. We can talk about it later how. But even when you trigger, you can see artifacts. So this is my final message. Just look at your data before you start processing it. I think the next speaker will talk about that even more. I have notable omissions. I couldn't follow everything that Carla Miller would have, but I hope you know diffusion a little bit better now. And I think that's all.
Thank you very much. I think the last point was very interesting about cardiac gating and triggering. I think not many people are doing. I think it should be done.